Okay, so we want to talk about magnetic materials. So first of all, let's go get a picture of a hysteresis curve. So this curve right here shows the magnetic, if you apply a magnetic field, what is the produced magnetic flux density that is produced? So let's copy this plot over. Okay, so what's going on is you're going to start at this beginning point. So let's say we're starting right here, okay? And so then what we're going to do is we're going to come in here and we are going to create a magnetic field by using windings or Ni to produce a magnetic field. So what's going to happen is that it's going to go up here and it's going to change the magnetic flux density until it gets to this point. If I keep going, it goes flat. So you see that's what's called saturation. So in saturation, what you end up doing is you end up getting all of your magnetic domains aligned, and then you can get no more magnetic flux density no matter how high you apply this magnetic field because there's no more domains to align. So let's go and look at what. So if we look here, this is, we can see that a magnet, you know, is built up of these little regions where they're almost like these little mini magnets, but they're pointing in random directions, so it's unmagnetized. When you start to apply a magnetic field in, all these are going to rotate to align. And so the more of these that you have aligned, the higher the magnetic flux density is going to be. Once all of these are aligned, that's saturation, and you can't get any more out. Okay, so this point hits saturation. Okay, so now what's going to happen is we are going to start dropping our magnetic field, and then it's going to come along to here. So at this point B right here, you can see that now I have no applied magnetic field, but I still have a residual magnetic flux density. And then you can keep going, and so then I'm going to apply a negative H. So I'm basically driving the field the other direction. I can go down here, and then I can get saturation in the opposite direction, and then you come back up here. And so you see you have this curve that looks like that. Okay, so we want to look at these magnetization curves, okay? So this kind of like what I was talking about is you take your magnetic material in here and you apply a really high magnetic field by producing a large current through a coil. And so you're basically applying the big current and then you move up to this point too, and then you remove it and you come down to this point, okay? And so then this point is your permanent magnet. So this is your permanent magnet point, okay? Now, in order to produce this permanent magnet, what you're going to do is you want a very large hysteresis loop. Okay. Now, most of the time, we don't want a large hysteresis loop. So here's showing two hysteresis plots, and you can see that this one is much more narrow and this one is much more wide. Okay, so for most of the magnetics that we want to do, we want a very soft material because we don't want a residual magnetic field. And so if I'm making a transformer or an inductor and then it goes up positive current, negative current, I want the area that this passes through to be very, very small. So the narrower this is, the less loss you're going to get in this hysteresis. If I want to make a permanent magnet, I want this to be really wide. Okay, so this is for permanent magnets. This is for switching things like transformers and inductors, motors, all of that. We want a very soft magnetic material. And again, this is permanent magnet. Okay, so that's first of all hysteresis, and the width of this gives us a hysteresis law. The next thing that we want to look at is eddy currents. So with eddy currents, you can see right here that if I have a conductive material and I move a magnet over it, it induces currents that travel in that magnetic. So if this is kind of like the bar of my transformer, my magnetic field is going to induce these currents in the magnetic core material. And if it's inducing those, then that's going to produce heat. So one thing that they do is the amount of heat is how big the wire loop is. And so what they do is that they make these wire loops, these sections very, very small, very thin, by laminating. So they put between these conductive materials, they put a thin layer in between of an insulator so that my current can't flow all the way around. It could just make these little areas. So let's go look at that. So you can kind of see right here, you can kind of see how it has these different sheets, and each of these sheets has an insulator between it. So you can kind of see these laminated structures. So they make these laminated structures to decrease the eddy current loss in the material. And then that's how you create the magnetic materials. So let's go look at some magnetic materials. So here is something on just straight magnetic materials. Let's scroll down and look at some materials. Okay, so here is straight iron. So straight iron has a relative permeability of 250. So 250, isn't super high. We'd like to get a lot higher, but you can see that this is the saturation point, so that it can get up to 22 kilogauss for my magnetic. And then we also look at the resistivity. So this resistivity is going to be related to being able to reduce the eddy currents. Okay. Um, so lots of motors use what's called silicon steel, and silicon steel, you see, it can go all the way up to 1500 compared to the 250, so a much larger relative permeability. It still has a nice high um, saturation, and it also drops the resistivity, or increases the resistivity, which makes it less conductive. Okay. So then we can go down and look at other things, and then we have what are called ferrites. So ferrites are ceramics. Okay. So if we look at the resistivity right here, you see, oh man, this is up to 10 to 10 to the 6. So this is way larger resistivity, which means that it's not going to produce eddy currents. So these ferrites are non-conductive materials. The problem, and they can have very high relative permeabilities, but lots of their biggest limitation is that they're very limited on their saturation point. So they saturate much lower. So these are like 3 as opposed to these that are in the 20s. So you can see that the steel-based ones tend to be much larger. So if I'm making a small little low current inductor, I would like to use a ferrite. Okay, if I want to do a big power transformer doing hundreds or thousands of amps, I want a high saturation point. So lots of times for motors and big power transformers, you use these iron-based things. For small inductors, you tend to use these ceramic-based ones down here. So those are the kinds that are typically used for most power-related applications.